Thanks, Steve, and thanks for staying around and hang out and listen to a little bit what I have to say. I decided to give a little bit different of a talk this time. I wanted to tell you a little bit about how we got into doing Skyline. I get asked this quite a lot, and it's actually not quite a straightforward thing on how you actually think about how you get towards coming from an analytical chemist, how you become someone who's actually working and trying to maintain a software solution for the community. So I don't think anyone needs too much of an introduction, but basically, the basics of shotgun proteomics is well known. We take a complicated protein mixture, digest it, separate it, and we perform this technique that's been used for a very long time called data-dependent acquisition, where we essentially collect a mass spectrum and we tell the instrument to make decisions on the fly about choosing certain most intense peaks to subject to tandem mass spectrometry. This technique has been absolutely incredible. It's actually allowed us to build these enormous lists of proteins. It's actually been also the sort of driving force behind making instruments faster and more sensitive. And now, of course, instruments can get to the point where you can do, instead of doing 3 MS/MS spectra, you can do 10. The speed of instruments and sensitivity of instruments has gotten absolutely incredible. There is a little bit complicating factor, and that is that these mixtures are really complicated. Of course, you don't need to really describe this, and this figure doesn't really do it justice. In fact, here's a narrow region of massive charge and a narrow region of time, and each of these little dots is a peptide, and there are literally thousands and thousands and thousands of these peptides. And so if you're trying to think about telling the mass spectrometer to select things on the fly, it's a little bit of a complicated problem that I'm not sure if we're ever really going to solve it fully. Because as soon as you get to the point where you've actually made the instrument fast enough, you're going to have a problem where somebody wants to put a more complicated mixture on it and run it in a shorter period of time. So it's kind of like this. So you get to the point where you get to the point where you're actually collecting chocolates off the conveyor belt. If you think about each chocolate as being a peptide, and you get to the point where eventually, if you ever watch this episodes of I Live Lucy, they eventually make the conveyor belt faster and faster and faster, and they're shoving the chocolates in their mouth and down their shirt to try to do everything they possibly can to keep up with the conveyor belt. So one of the things that I've always wanted to do is, actually, I've never really been that interested in having how big of a list of peptides I can identify or how many proteins I can identify. What you really want to know are what are the important things to be able to track. And you want to be able to follow and make comparisons between samples. So you can easily sort of do these sorts of experiments. We've done a lot of these label-free quant. We've done a lot of stable isotope labeled experiments. But this is just kind of an example where we want to focus on this peaks because it's gone down from here to here. It's gone up from here to here. And this one's just gone down, et cetera. And then we can use, of course, our MS/MS spectra to try to annotate these differences. So, using accurate mass and high-resolution data in the MS1 mode has been really kind of a powerful approach for us. And it's, in many ways, you're taking a targeted approach, but you're just kind of first looking at what's different, and then you're trying to assign things as far as where your effort is going to be to try to focus on your identifications. So what do I think some of our challenges are for proteomics? If our goal is ultimately trying to compare very large numbers of samples between large numbers of conditions, and to be able to do this in a robust way where we can compare this between days, between weeks, and between labs, it's actually a really complicated problem. And so I think some of this that we have to do is actually sort of unlearn some of our so-called bad habits. So bear with me for a little bit. So first off, I think data-dependent acquisition analysis of peptide mixtures complicates quantitative proteomics. So we've sort of had this semi-random approach for collecting data, and we're trying to compare it in multiple runs. And of course, we don't sample the same peptides in multiple runs, especially if there's major differences in intensity. So in general, people like to be able to say, we've identified these peptides in a given mixture. And I think, it's generally a bad idea to use semi-random sampling of a mixture to assess presence or absence. We, of course, can assess presence, but then it gets to the question is, can we begin to start assess absence? And absolutely not. If you're using a semi-random approach to collect data, we probably can't. And there's also this general rule of thumb in any sort of analytical chemistry that you sort of can't define detection unless you kind of first assess or define your limit of detection. So this, of course, requires standards and careful assessment of validation of basically your assay. And the other thing that people often like to say is there's a lot of times people throw out the word quantitation and quantitative proteomics. And the only way that something can be quantitative if you've actually demonstrated that the measurements that you're making are within the linear response within the measured intensity. So if you have 2 points, are you sure that both of those points are within your linear dynamic range of your measurement? Is one of them below your lower limit of quantitation? Is one of them above your upper limit of quantitation? And in proteomics, we talk about relative quantitation, but it actually may just be differential analysis. We've just been teaching a short course this last day or so, and this is one of the things we harp on a lot. So proteomics also has a culture where building lists appears to be more important than building and validating assays. Pretty much every single other field in mass spectrometry focuses on building an assay, validating the performance of that assay, then working on what it takes to disseminate that assay to other labs. I think we're really going to have a hard time as a field if our figures of merit come to be how many peptides we identified. So these are things that I think that ultimately we actually have to do. We have to be focusing on what are the figure merits of our measurements and how we actually go about disseminating those measurements to other labs. So would it be better to take a targeted approach? So this is something, again, I don't really need to describe this too much to this audience, but that one of the approaches we've often taken is using triple quads, and our field uses a lot by measuring a precursor and product ion transition. And you can measure multiple of these ones, and then just like Al was talking about earlier, you sort of have this chromatogram-centric analysis, right? So you have this precursor and product ion side transitions, and you have this combination of transitions gives rise to provide our confirmation that we're measuring what we think we're measuring. And you can use the relative intensities of these again to provide comparing it relative to a spectrum library to even improve our confidence even more. So it's really powerful because these triple quadrupoles are just outstanding instruments. They're really sensitive, and just looking at dilution of a peptide in human plasma, basically you have incredible linearity. You can keep diluting the sample and going down, and it comes out off the line a little bit at the low end, but you can measure very low levels of peptides in complicated mixtures. And I'm not saying this happens for every single peptide, but I'm saying that you can get this quite frequently, and if you're careful, you can get really low limits of detection quantitation. Okay, so I had already convinced myself that it is very important to measure things in a targeted way. We often collaborators come to us and say, do this enormous proteomics experiment. The first thing they're often saying is, how come these 5 proteins I know a lot about my system aren't in your list? So it began to make me think, well, maybe we should start with those first 5 proteins and start to come up with assays to quantify them first. So the big problem was that when we first started this in 2006, software for building targeted proteomics methods just didn't exist. Neither did software for the analysis of complex multiplex SRM methods. There were a lot of cases, a lot of this software was designed to measure a couple compounds in thousands in samples. They were not designed to measure tens or hundreds of peptides in tens and hundreds of samples. So it was a little bit of a difference in a paradigm shift in how we need to think about building these things. And the other important thing is that no software was capable for cross-vendor data analysis. And I really felt that this was important. We really need to be able to take some of the analysis tools away from the vendors, no offense to the vendors, but we need to be able to demonstrate that we understood how the tools were processing the data and put the hardware on an even playing ground to make comparisons between the instruments. So out of desperation, one weekend, trying to come up with my list of all the transitions you can measure, I wrote a piece of software to do this, basically paste in a peptide sequence. You could calculate the features, and you can calculate the masses and fragment ions, and you could then spit that out to then measure in the instrument. There are a bunch of problems with this. It was extremely crude. It was one protein at a time. It could only generate the methods, and we knew it ultimately at some point in time we had to link up the generating the methods with the measurement of the results. It would be completely impossible to maintain, and it was developed by myself, and I'm definitely not a programmer, and while I can write some basic programs and understand what our software engineers are doing, it definitely was not developed at a level in which I knew that this could be maintained and used regularly. So the downside and the problem was that 2 miracles needed to occur. We had this great plan for what we really wanted to do for software. I was a brand new assistant professor, had no resources, and really didn't have the people and capability to do this at the time. So one is we needed money, and this was a major miracle that needed to occur when you're a brand new assistant professor and you're just kind of really getting going. And I need to find a professional software engineer capable of building the platform we were dreaming of. We wanted to have a graphical user interface, and we actually ideally wanted to have, this makes it even more challenging, someone who knew something about mass spectrometry. So who said there was no such thing as miracles? So it was actually really quite amazing. Dan Liebler stepped in after just a couple discussions of sort of discussing these. I pitched this wild idea to him at an ASMS in 2000, I think it was 2007, about what we wanted to do, and he said, well, what would it take to make this happen? And next thing I know, he's actually carving out a part of one of his grants to help us support some of his work. I'm really indebted to him to kind of making, and sort of, it's always a lot of the field in kind of at least getting this going. And then about a week right after that ASMS, Brendan McLean showed up in my office saying and Brendan, if people don't know a little bit about his background, he'd been developing software for easily 20 years with background at Microsoft and several other major software companies. One of the things that's kind of funny is we talk about how Skyline now has 20,000 installations, and he kind of jokes and says, he's like, I'm actually used to software installations on the millions of levels, so he's definitely got a lot of experience building big projects. So a little bit about what we did is we wanted to make the software protein and peptide centric. We wanted an intuitive document interface, multi-level undo support, direct analysis of all triple quad data, vendor neutral. We didn't want to have any file conversion, ability to choose peptides using discovery data, free and open source, and developed professionally. This was a really ambitious set of needs, and I think we've kind of met them all and exceeded people's expectations in what we did. Just to kind of give you a sense, the growth has been huge. We first released it in June of 2009, and we're now getting about 800 installations per month now. And just to show you that it's not just installations, this tells you how many times it gets booted up every week. We're now getting booted up about 4,000 times a week. And there's also a lot of other interesting things that come out of this. You learn that there's not many people doing mass spectrometry during ASMS because there's these dips. But there's also, during the holidays, it really seems like nobody's doing mass spectrometry either. So initially, we wanted to make it vendor neutral. The only instruments we had access to at the time was the instrument that we had in the lab, which was a TSQ Ultra and a applied biosystem from Manny Polovich's lab. We were able to display the data comparatively between it, and then first thing we did was go out and see, okay, what other instrument data can we get? And I'll point out right now that Agilent was one of the first companies to kind of jump right in. They provide us with data. They provide us with academic collaborators. They also just really embraced this as being, even though it was an academic project, and most other companies began to feel a little bit threatened by it, they actually really kind of adopted us and kind of embraced this open source project as a platform. So in the last year, we've had, in fact, it's been a little bit more than a year, we've had this really incredible collaboration with Agilent. And a lot of cool things have kind of occurred in Skyline that a lot of people don't know about, and it's largely because of this collaboration with Agilent. So first off is they approached us and said, look, we'd really like the ability so that within Skyline we could call external tools, particularly their tools. And the thing is that they were very open as to opening this up to everybody and to every type of tool. So just to give you an example is that you can actually paste things into websites and analyze things into websites outside of Skyline directly from this. And this was, again, a feature that directly came out of this collaboration with Skyline. So here's an idea of the SRM collider. We also could call any sort of exe program, batch file, command line, Perl, Python program from the command line. So we've also done R scripts. You can pass arguments. You can set up a transition report that you can pass to any program. And again, this came out of a feature request that came from this Agilent collaboration. Also, Agilent said, look, we'd really like to be able to call Skyline from our software. We need to be able to run this peak integration programs, be able to generate reports, et cetera. So this, again, started a whole other aspect. We had this great graphical user interface, but we know that people wanted to run these things in batch mode. And Agilent really kind of gave us the capabilities and the incentives to do this. So we can now open and save documents, import results, all from the command line, from other programs. You can export methods. You can also customize the toolbar specifically directly based on vendors if they want to add features or capabilities or external tools can be added externally to Skyline directly from this. So the other thing, there's been a lot of hype, of course, with data-independent acquisition recently, and most people don't realize that Skyline supports data-independent acquisition across all vendors. It doesn't matter what platform you're using, but what we spent a lot of time doing is trying to make sure all this worked for Agilent QTOFs. And just to kind of give you a little bit of sense of what it is, it basically, instead of sitting there and doing data-dependent acquisition, we actually just have wide windows that span a range of 10 or 20. That sit across a given mass range, and then what we do is we essentially extract. We do MS on those windows in a systematic, reproducible way, and then we extract precursor and product dyne chromatograms from that data. So the data in the end looks just like SRM data, except it's done on everything all the time across the entire mass range. And again, you use these multiple different product dynes to be able to give you confidence that you're measuring what you think you're measuring. One of the powers of this is that you often gain better sensitivity. So we also in Skyline can always plot the MS1 data and the MS data. Here's showing the different isotope chromatograms, the M, the M+1, the M+2 isotopes. And there is interference here in the MS data, but in the MS, well, we have a little bit of less sensitivity. We lose the background faster than we actually lose the signal. So we gain a signal to noise. Just to show you an example, here's a dilution curve. There's multiple different, it's about twofold dilutions or so in a BSA digest, showing the lowest level to all the way up to the highest level. You can integrate the peaks. You can look at all different. One of the great things about Skyline is this rich graphical user interface, dockable windows, et cetera. It's very customizable. And you can look at it and compare things to spectrum libraries to show that you're measuring what you think you're measuring. Here's actually the relative fragment intensities of from a spectrum library. You can also, something you can't do with other competing software tools is you can't look at the fragment ion data and looking at the precursor ion data. We can definitely do that. We can do that for Agilent data. We can do that for every vendor's instrument hardware. And you know, Waters has their MSDE, but on Agilent QTOFs, you can do the same sort of thing. You can essentially just do fragment all, do low, high energy, or you can do low energy and multiple different high energies. And Skyline is smart enough to be able to extract that data, and you can then plot, of course, your precursor ion chromatograms, which are the top 3 most chromatograms at the low energy, and the higher energy is showing the product ion chromatograms to provide structural confirmation. You're measuring what you think you're measuring. So one thing I want to point in the last couple minutes while I'm talking to you is that there is a major challenge with precursor selectivity in doing these data-independent acquisition experiments. If you won't always hear about this in all cases, but I want to make sure that this is very clear for people because it's something that's underappreciated, I think, because there's a lot of hype about using 25 mass to charge wide windows. So if you're using this peptide and measuring this peptide with a 2 mass charge wide window, you sort of get a spectrum like this. If you do a 10 mass charge wide window, you get a spectrum like this. 20 mass charge wide window, you get a spectrum like this. And even with accurate mass, it really doesn't matter. You're still going to end up getting lots of interference. Just to kind of give you another example, here's this same peptide again, shown in the chromatographic time scale. If you open it to 20 mass to charge, you end up getting, here's that same peak, but then you have another component here. And it becomes very hard to distinguish between the two. They're both within the window, the 10 mass charge wide window. The other interference is outside this window, and with a 20 mass charge wide window, they're both measured simultaneously. So here's just to show you another example of how challenging this is. So here are 2 different peptides. It's a 10 mass to charge wide window. Here is the, this peptide right here is this is the oxidized form of the same peptide sequence that's over here. There's this difference in 16 Daltons, which is 8 mass to charge. They both fall within this 10 mass to charge wide window. And of course, almost all the fragment ions have the exact same elemental composition. So no matter how much accurate mass you end up having, you're never going to be able to distinguish between them by mass alone. So you end up relying on precursor selectivity and chromatographic retention time. So this is just an example of how complicated these data can end up being. So here's how we're actually beginning to proposing to solve this. Basically, we have this normal idea of essentially a 20 mass charge wide window, and you can improve the specificity by going down the 10 mass charge wide window. What we'd actually like to be able to do instead is to shift the windows by 10 mass to charge. So you measure the first spectrum with a 20, they're all with 20 mass charge wide windows, but in the alternating sets of cycles, you shift them by 10 mass to charge. And the reason why this is powerful is now in the target that you're actually interested in, you see them in all possible windows, but the interferences are present in one, it's absent, it's present in one, it's absent, et cetera. So basically, this is what it looks like if you don't offset the windows. You see 2 different chromatographic peaks that cause interference. If you alternate the windows, you see data that looks like this, where the interference is zigzagged. And we can use computational algorithms very similar to Hadamard transforms, where we treat this offset as similar to like a mask. And we can also then completely, so here's what the data looks like with this alternating window. And when we deconvolute it, we get data that looks like this. So we can completely deconvolute the data. We can collect 20 mass to charge worth of data and get specificity worth of 10 mass to charge without actually having any issues and effect on quantitation. Of course, you could do this with 10 mass to charge and get 5 mass to charge worth of specificity. It just, in selectivity, it all just depends on what you're interested in. Okay, so this one last thing just to kind of show you is that here's the MS1 data. Here's a lower limit of quantitation for 21 peptides spiked into a lysate. When you do the MS-MS at 10 master charge wide isolation windows, you get a lower limit of quantitation using all the fragment ions. And with the demultiplex, you get very close to the 10 master charge wide specificity. With a 20 master charge, you have nowhere near the lower limit of quantitation. When you just use the top 3 ions, you get much lower limits of quantitation, largely because there's less interference. And then again, the demultiplex data is very similar to the 10 master charge data, but much better than a 20 master charge data. And same thing with the top 5 and the top 7. Okay, so definitely have a lot of acknowledgements. Of course, I'd like to thank my colleagues at Agilent. There's way too many to list. I actually started writing out a list of all the names. I realized I would probably take up half the slide. So it's just been an incredible group of people to work with and just to talk about science and mass spectrometry. So within our lab, Brendan McLean, of course, has pioneered a lot of software engineering. A lot of the algorithms came from Jared Eggerson. A lot of the thinking about how to sort of analyze these data came from Rich Johnson. The initial idea of overlapping the windows was Sonia Tings, who was a graduate student in the lab. Dario Amadei, he implemented the first deconvolution algorithm. He's an incredible person with a signal processing background. And of course, I'd like to thank you for all your attention, and I'm happy to answer any questions.